Hi again, everyone. Welcome to session 3 in nutritional biochemistry. And today we are going to go through fat soluble vitamins and few of the macro minerals as well. So again, I request that you all go through these activities when we have finished the session. Watch some of the YouTube videos and some links that I'll be posting at the end of this week. So you might, I don't want to, but you might get overwhelmed that we have to cover these many nutrients today. But remember when we were doing lipid absorption, I did share that absorption of all fat soluble vitamin is kind of similar. Okay. So we would be a little faster. I won't be repeating that bit. But we will talk about individual nutrients, their food forms, which is the chemical form that our body uses for its function, and what are the name of the transporters and cofactors. Okay, so tell me, what do we know about vitamin A? What are its food sources? What are its functions? Why not you start off today? Anybody?
So it's found in liver.
Yes, so very good. So the food form will come in the liver and it will be joined to a fat and a protein molecule. And any important function, if anybody can recall? Function in a human body?
It's important for eyesight.
Yes, correct. That's correct. Yes, Mary is also right in the chat box that it is important for eye health. So let's explore a little bit more and or maybe refresh from your previous knowledge that it is a group of fat soluble retinoids. Okay? That's what we call them. So there are a number of vitamin A. And what are actually? They are in a chemical form retinoids, which includes retinol, retinal, and retinyl esters. And I'll explain the structure in a second. Now, in the food forms, just kind of I'm just want to flag out that couple of things I've added in these slides. So apologies. You can just add them in your notes. So the forms are, one is preformed vitamin A that you just mentioned, that it is present in the liver. So that means preformed means it is ready for its action in our body. It's ready to do its function in our body. And this is the esteride form. What do I mean by esteride? That it is attached to a fat molecule. Okay? So retinyl ester is the same thing as the fat form or the preformed vitamin A. Then the second form we classify as provitamin A carotenoids. I'm sure you all must be aware that they are alpha carotene, beta carotene, and our body has to do some effort to convert it to its ester form, because body also uses it in its ester form. Okay? So that's why vitamin A from carrot or sweet potato, pumpkin, they are all we are calling as provitamin A carotenoids, because our body converts it into retinol or retinyl ester. Do we know, can body convert 100% of carotenoids into retinol? Is all the beta carotene in the carrot converted to retinol in our body? No, it's just 50%. Okay. So these are the forms that I was talking about. So just adding. So you can see my animation have shifted quite a bit because I added this sentence here. So retinol is OH group. Retinol is when to the entire structure, we have a CHO group attached, and retinoic acid is COOH. Then you must be wondering, what is retinyl ester? So that is CO, and R is the fat chain. Okay. And as you rightly mentioned, that vitamin A is critical for vision because it is essential component of rhodopsin. That is a protein or a pigment which absorbs light in our retina. Then there is also evidence that vitamin A supports growth of the cells, their differentiation, and maintains various organ systems. Now, another very small addition just to let you differentiate between provitamin A and the other carotenoids, because it is only these carotenes that our body can convert to retinol. So alpha carotene, beta carotene, and beta cryptoxanthine. But our body cannot convert the other carotenoids into retinol. However, we all know that they are all wonderful. They are amazing carotenoid. There is enough evidence that lycopene, when absorbed from tomatoes in a cooked form, may reduce risk of prostate cancer. And lutein and zeaxanthin are also important for eye function. Okay, moving on to the digestion and absorption. As you would notice, I've added few animations. So again, I'll go slow by slow, and then it will be kind of similar for other fat soluble vitamins. So now remember my favorite carrot cake for morning coffee and cake. Okay. So let's say I've consumed carrot cake. Tell me, what are different forms of vitamin A you would find in a carrot cake? So what are the different forms of vitamin A that are present in carrot? Oh, sorry, carrot cake.
The carotenoids.
Thank you. So we have beta carotene. What else? Yes, Annie is also right. It's carotenoids. And if it has, it is made from avocado, then it will have omega-3. And if it has been made with egg yolks, then it will have retinoids as well. Okay. So we are consuming all kind of vitamin A. And it is bound to protein as well as fat. So as usual, the first step is that the enzymes pepsin and proteases, they remove the protein portion so that we only have carotenoids and retinyl esters. So as I just mentioned, retinyl ester means that a fatty chain is attached to it. So that fats are now removed by other enzymes in the gut, such as esterases and lipases. So body is doing all that effort so that we have free carotenoid and free retinol available for absorption. And where does it go? It all gets attached to bile so that we form a micelle. So it's the same thing that we did in the lipid absorption. So the first part is easy. Now moving on, what's happening inside the cell. So now you can imagine that I am consuming beta carotene also, I am consuming retinol also. And I might be consuming some other carotenoids also if I've added, let's say, orange zest in that carrot cake. So now look at the amount of work this intestinal cell is doing. Let's go from top to bottom. Beta carotene can be converted to retinols. And then that retinol can be converted to retinoic acid, which our body can use, and it will travel to the liver. But look, if I have got retinol, then we have these enzymes called as cellular retinol binding proteins. What is happening is, again, body is trying to convert it back to its natural form so that it can use it. So a fat group is getting attached here with the help of these enzymes, LRAT. And then I'm converting it into a ester form. Again, I'm making a retinyl ester. So you can see it's written retinyl palmitate. But if I've consumed avocado, if I have consumed some walnuts, then it will be retinyl oleate or retinyl linoleate. So whichever fat I'm consuming, that will be incorporated here. Okay. Then all these forms. So you can see body is not letting anything go waste. All the forms of carotenes and retinol, they are again getting incorporated into chylomicrons. Now, as I mentioned, retinoic acid can travel to the liver, bound to albumin, and all other carotenoids, they get attached to chylomicron. And as you would recall, they all travel in lymph. Okay. Now, just one step, which I did not speak so far, is that this retinol that we are making from beta carotene, there are two fates for this molecule. Either it can travel to liver for further processing or storage, or we have the same enzyme that can, in the presence of niacin, convert it to retinol. Why? Because body wants to make retinyl esters. So, and it is all happening in that small molecule, amazing intestinal cell. So now the same steps have been written in this slide, that first we have to break away the fat and the protein from whichever vitamin A source we are consuming. After that, everything gets attached to a missile and simply diffuse at the brush border. Intestinal cells are very specialized, they are smart, they can make all the conversion between various forms of vitamin A. And for that, they use cellular retinol binding proteins as well as lecithin retinol acyl transferase. So you can see transferase means it is transferring the fatty molecule, the fat chemical structure to retinol. And then everything gets attached in a chylomicron. So that means very low density lipoprotein, low density lipoprotein, and high density lipoprotein, LDL, HDL, they are all carrying vitamin A. So these were different retinal esters. They can be used by different tissues in our body, or it can be stored in the body, and the storage form is called as stellate cells. We love proteins, isn't it? Because they protect all these nutrients. So for vitamin A, we have these two proteins, retinol binding protein and transthyretin. They all are getting attached to the vitamin A when it is moving around in the blood. Some of the agonists. So when it is attached to retinol binding protein, we have noticed that zinc is required for optimal function of these retinol binding protein. So it becomes an agonist. Iron is required for conversion of beta carotene to vitamin A. That's why, people who are deficient in iron, they may also be deficient in vitamin A. So they both coexist many times, especially in children who are malnourished or pregnant or lactating women. And niacin, because niacin is required when intestinal cells are converting retinol to retinol esters. Any questions at this stage? Let's take a full minute and go through these steps. Write the sequence, highlight the name of the enzymes or the binding proteins. And let me know if you want me to repeat any step. Okay, what happens if somebody is deficient in vitamin A? Any deficiency signs or symptoms anybody is aware of or has any recollection? So Jane is commenting on poor night vision. That's correct, Jane. Anybody else? Blindness, very good, Vanessa. Yes. Has anybody heard of dry eyes? So it has a very scientific name. So thank you, Courtney and Michelle. That dry eyes, it is called as xerophthalmia. Okay. I know it's a very technical name and I am kind of really stretching you all, but we need to be aware about these technical terms as well. So that's what we call as the first stage of vitamin A depletion. So as you are aware, it is a fat soluble vitamin. It is stored in the liver. So how long does it take for those deficiency symptoms to appear? How do we measure that? So this research was done in around 1960s. And what they did was they fed somebody vitamin A, and it was a human study. And then for 3 or 4 months, they did not give them vitamin A rich foods. So a very normal diet poor in vitamin A was administered for these people. And then at the end, they were assessed for vitamin A deficiency. So it was noticed that if we don't consume vitamin A rich food for 3 months, then deficiency symptoms will be observable. So our stores can help us out for 3 months. Yes, Michelle is saying that she had dry eyes when she was living in cold climates. And you know, I had dry eyes a couple of years ago when I was driving in Adelaide summers. So I'll have my aircon on at the fullest. And then I noticed I started having teary eyes, itching, and dry eyes. Uh, until again, I made a self diagnosis that for some time I was vegetarian. I was not consuming enough vitamin A rich greens or carotenoids. Yeah, so I kept myself on vitamin A supplements, and within a week, I could see that dry eyes is not happening. So another reason, you know, when we are taking our clinical history with our clients, talk about lifestyle factors, you know, so that they share as much and you can gauge from those symptoms and those lifestyle factors that may be contributing to deficiency of any of these nutrients. Okay, let's move on. One of our favorite fat soluble vitamin nowadays, or maybe always, because it is synthesized when we go out in sun or we are sunbathing, we are enjoying family time on the beach, and we are thinking that our body is making vitamin D. So vitamin D is a hormone, and there are two major forms. One is we call as ergocalciferol. That is the one which comes from some of the plant-based food, such as shiitake mushroom. And this is the D2 form. Okay. Then we have vitamin D3. It is called as cholecalciferol. Sorry again for vitamin D. Be very careful because I will be speaking these terms. There's so much confusion out there. So many new brands coming up. So just trying to understand what are these different forms. So I'll be speaking the entire name. Now, these two forms are not the active forms. That means our body cannot use it to do its function. We will see now what happens and how body activates it. But the active form that we use is called as calcitriol, and chemical structure is 1,25 dihydroxy cholecalciferol. And it's written later in the slides as well. Okay. And you have so many agonists here, and we will just understand how they are agonist. Remember, magnesium is a big agonist. Functions, we all know it's how important it is for bone because it supports calcium absorption. Then it also supports phosphorus homeostasis. So if our body has to use phosphorus, absorb phosphorus for food, we need vitamin D. Then different cells, immune cells especially, when they are dividing, when they are, all immune cells and red blood cells we make from stem cells. And when they are being differentiated into their different forms, then we need vitamin D. In fact, some of the immune cells, they can activate vitamin D. What do I mean by activate? That means they can convert it into this form. Okay. So I might have gone in the sun and I might have vitamin D3 moving around in my body, but immune cell cannot use it. It has to activate it to 125. So immune cells can do that. Now there is something written here, non-genomic intracellular signal transduction pathway. Quite a tongue twister, isn't it? The simple meaning is the cells, they talk to each other. There is a signaling going on. Remember in session 1, we talked about insulin signaling pathway? So there were some long names there, phosphoinositol, blah, blah, blah. So such signaling pathway, they need vitamin D. We don't know yet how it is helpful, but that's one of the non-genomic function. That means it is not causing gene expression, but it is supporting those signaling pathways so that there is continuous chatter among different cells and they continue to help us. Okay. Then genomic mechanism is when it is influencing gene expression. And how do we know that? Because now it is noticed that most of the human cells, and I'll again use the example of immune cells, they have vitamin D receptors on their cell membrane. So they need, so for example, again, there is a virus infection and a particular immune cells need to do its role. Vitamin D gets activated and it goes and attached to these receptors, and it is then that immune cell start preparing as a fighter. Okay, it becomes that knight that has armor and now that can fight the infection. Interesting, isn't it? Has anybody heard anything, seen any webinar regarding vitamin D during these COVID times? There is a lot of research coming out that it is important for us to have a good immune system, and that needs vitamin D. Yeah. Okay, so Annie is saying, yes, there is a lot of data about that, and especially about how we are converting it from sunlight. So this diagram or flow diagram is telling us how we are synthesizing vitamin D from the skin. And when I say synthesize, we are also discussing how we are activating it. Okay. So if I have consumed shiitake mushroom or mushroom toast today in the breakfast, I still can't activate it because it is a long process. So let's again go one by one. Now skin, we all know, has got a fatty layer, isn't it? So that cholesterol is first converted to 7-dehydrocholesterol. And when does that happen? When I go out in sun and exposed some of the, it may sound really stupid, but fatty areas of my body to the sun. For how long do we have to do that? Would anybody help me out? How many days a week? Okay, so I have so many answers in the chat box. Thank you. Annie, Michelle, Mary, you're all right. About 15 to 20 minutes. Megan is saying every day. That would be the best. But minimum 3 days. Okay. And can you see that I've written a particular type of UV rays also here? So I've added that you don't have in your slide. So there are different type of UV rays. Some, the harmful ones, the ozone layer, it can absorb it. And we can make vitamin D only when we are exposed to UVB. And there is a particular wavelength as well. And that time actually is around, 11 to 12. When we are in our office, staying away from sun. Okay, moving on. That's the first step. So now that 7-dehydrocholesterol is converted to what we call as pre-vitamin D3 because it is not that active form now. So I'm talking about step 2 now. So this now moves around, this pre-vitamin D3, it moves around in the blood. And always protein, good quality protein is so very important because it is bounded to vitamin D binding proteins. The way vitamin A was bound to RBP, retinol binding protein. So here we have vitamin D binding proteins. Now, can you see that there is an addition here? Chylomicron, dietary. So that means if I have taken any food source such as fatty fish, let's say, or I had taken shiitake mushroom, or I had taken any supplement form which was not activated. Okay, so supplement form also comes in various forms. All that also travels together. So it all comes together, and where is it going? First step is in the liver. And here, now remember the cofactors of your column in the table, write down, we need vitamin B3 because niacin gives away its hydrogen to vitamin D in the presence of cytochrome P450 enzyme. And these enzymes, please write down, they need iron. They are in the liver and we'll talk about them again in session 6. So for here, remember that cytochrome P450 carry out hydroxylation reaction and they need iron. But this step of vitamin D activation actually also requires magnesium. Now we have made 25 hydroxy cholecalciferol. Can you see what the body is trying to do? What is this hydroxy? Hydroxylation, hydroxyl. What is body doing? What is body is trying to make it water soluble? It's a fat soluble thing. Body is adding that hydrogen. Yes, thank you, Jane. You're right. Yes. So it is because ultimately it is a hormone. It has to go out to various peripheral tissue and cells. So it has to be water soluble. Okay. Now again, this 25 hydroxycholecalciferol can stay in the circulation for about 15 or more days. So when I'm going to get my blood test about my vitamin D status, this is what I am measuring. So this tells us how much potential I have to make active vitamin D. And this is the form that I am storing also, right? And this form can also do various functions. It can do those non-genomic function. It can also help a bone formation. But remember, I talked about that gene expression function that can only be performed after the second activation. And look, where is that happening? In the kidneys. So we are again using the same enzyme. It is a different form. You don't have to remember the numbers because cytochrome P450, actually we have got about 50 or 60 of them. So just remember magnesium dependent hydroxylase. Okay? And that is where we convert it into 125 dihydroxy cholecalciferol. It is also called as calcitriol. And its half-life is for 4 to 6 hours. What does that mean? Half-life. That is for how long it can. Yes, Michelle, you are right, kind of there, that it is available for about few hours and then it won't be effective. Yes, in about 4 hours, it will be left to its 50% and another 4 hours, nothing. So it has to be utilized. And how it is utilized? It goes and attaches to its vitamin D receptors and helps in the formation of different cells, differentiation, and all other gene expressions. As you know, there is so much data now that people who have Alzheimer's, so there have been some correlation studies. So they looked at the people who had Alzheimer's and they looked at their vitamin D status. Similarly, they looked at multiple sclerosis and looked at their blood status and some other autoimmune conditions as well. And they found that these people are vitamin D deprived. So, and now, you know, in last 20, 30 years only, not only 20, around 15 years, we have understood how every immune cells has got vitamin D receptors. And vitamin D is so imperative for gene expression. And yeah, so you can see how long is that process. So is this activation process clear? How we are making vitamin D from cholesterol? Anything you want to ask me at this stage? Right. Feel free to revise it. Watch a video which is given on LMS and shoot me any questions on the loop or anywhere else. Okay, Annie is asking that UVB rays for 10 to 12 minutes and that has to be without sunscreen. Yes, in my understanding, some of these sunscreens, they are blocking that very main UV rays, isn't it? So yeah, that's why there is so much exploration for the other zinc-based protection. That's a very good question, Annie. Do we know the benefits of this compared to skin of cancers as numbers? That's a very important point. I don't recall any data in about the number. But yes, there is a potential of exposing skin to harmful radiations for a long time. And then, especially people who are genetically predisposed getting cancer. What do you say? Does anybody want to add anything here? Has anybody read? Because I'm sorry, I don't have the data in numbers. But I'm just trying to think that maybe we try to use zinc-based UV protection creams, or we consume highly antioxidant-rich food so that it can balance out that exposure that we may have. And zinc in itself prevents DNA damage because it is a component of, and I'm going to repeat this next week, zinc is a structural component of DNA damage repair enzyme. So our body has these DNA repair enzyme. So yeah, but sorry, I don't have the answer, but I'll have a look. I'll try to look at any study who has looked at these numbers. Good point. Okay, moving on. So absorption, this is the food-based vitamin D that is coming. As you would already know now, that it is getting attached to micelle. Sorry, body does not have to do any digestion here. In the intestinal cell, if they want to use it, they will use it. Otherwise, it will get attached to chylomicron and travels in the lymph system attached to chylomicrons. Moving on to vitamin E. We will take break when we finish fat soluble vitamins. Now more forms. So vitamin E actually includes 8 vitamins. So we have what we call as tocopherols. So we have alpha, beta, gamma, and delta. It is the alpha tocopherol. Please highlight this one. This is the one that our body uses and loves. And it has greatest activity, means that it has the potential to carry out its function in our body. And its deficiency may lead to hemolytic anemia, loss of vibratory sense, weakness, and some people, you know, in their skin, they may have some brown spots. So that is an indication of deficiency of vitamin E. Okay, then the other form is tocotrienols. I'm not sure whether that's the correct pronunciation. That's how I have learned to pronounce it now. Tocotrienols. Okay. Now, you must be wondering that in the agonist we have written high dose of vitamin E. Why? And why vitamin K? Any speculation? So vitamin, okay, I have some answers in the chat box. Let me read it. Yes, Jane, you have nailed it. With vitamin K, it is a competitive inhibition. What about high dose of vitamin E? In my understanding, you know, excess of vitamin E can be problematic. So that's why the intestinal cells are kind of tuned that if it is too much coming, I don't have to take it inside. There is enough in the blood. Okay. So that's what I have kind of understood so far. Coming to the absorption. So tocopherols, they are found free in foods, but tocotrienols, they are esterified. So now you know what is the meaning of esterified, that it has a fat molecule attached to it. So the same story. What will the body do? It will consume tocopherol straight away, but tocotrienols, body would have to remove those fatty group. And then what will happen? it will get attached to micelle, and in the intestinal cell, we can make these forms again, and everything get connected to chylomicron, and then again to your HDL, LDL, VLDL. So tell me, I'm saying that all these fat soluble vitamins, they are getting attached to HDL, LDL, VLDL. And if I go for a cholesterol test, and my report comes that I've got really high LDL and I've been advised to take statins, what do you see as a clinical implication? Will there be an issue with absorption of fat soluble vitamins? What advice you would give to such a client, or it won't be an issue? So Juliana is saying, yes, it may lead to fat soluble deficiencies and impact vitamin E absorption. Yes, Jane. So, I tried to look at the research, and if some of you also had time, have a look. Most of the randomized control trial, they are saying that statins, they actually inhibit the body's de novo cholesterol synthesis. So you all know our body makes cholesterol, okay? And there is an enzyme that we use there, HMG-CoA reductase. So again, I'm trying to reinforce your biochemistry from bioscience. So they say that statins, they inhibit that cholesterol. So this one may not be impacted that much. But then I read this slide, read all these notes. So that actually means there would not be sufficient cholesterol in the skin to make active vitamin D. Isn't it? So I'm actually not convinced with all that research. So I'm just sharing with you that we have to be really critical when we read articles and try to look up the processes on our own to make that clinical judgment. I hope I haven't confused you. So the intention was just to make you aware what is in the literature. Okay. So now all this vitamin E may lead to liver, and liver actually is biased towards alpha tocopherol. That's why I said our body loves it. And there is a special transporter protein to carry this particular form, alpha tocopherol. And this is what is released in the blood. So the primary form of vitamin E is alpha tocopherol. That's the main thing to remember. So you can see the absorption is quicker now because we are repeating a couple of things here. Let's move on to vitamin K. Again, different forms of vitamin K are available. The one which we are consuming from plant sources, such as phylloquinone, they are called as K1. Then we have menaquinone, which our body can synthesize. So our amazing healthy bacteria in the gut, they can manufacture menaquinone. And then synthetic form is menadione. What is the importance of vitamin K? Its functions in our body. Would anybody like to comment? Very good, Tracy and Mary. And Jane also has got it there. Blood clotting. Yes. Anything else? Has anybody heard that one needs to take vitamin K2 for bones? Oops, sorry, I just messed up with my screen share. Just a sec. Okay, now let's see. Yes, Vanessa, very good. Courtney is also right. Megan, you got it there. Bone synthesis. Very good. So what's happening is that vitamin K supports these what we call as carboxylation reaction. So for the clotting also, we use it for the same enzyme. So prothrombin is converted to thrombin, which are the clotting factors. And I wish we had more credit point in this subject so that we could go through that pathway, but we can't. So it is not in the purview of this subject. So there we need vitamin K for carboxylation. And then when we are making new bone cells, K2 by the same process of carboxylation, it supports osteoblastic activity. That is the bone cells. When they are being made, we need K2. So if you have a client coming to you in future who is at risk of osteoporosis, please include vitamin K rich diet for them. Or if you are planning to give them vitamin D3 supplement with calcium, remember it also has K2. What are some good sources of vitamin K? Okay, I leave it up to you. Green leafy veggies is one. Fermented foods, Mary is saying. Okay, Mary, I'll have to check that. Okay. Yes, it would make sense, I think, because then it will support the bacteria in the gut. Yes, yes, fermented foods are in, definitely. Eggs, yes, eggs are also rich. Okay, moving on. Yes, do I have a question there? Okay, no issue. Coming to the digestion and absorption. No digestion for phylloquinol. They are simply absorbed with micelle by diffusion. Now, menaquinols that are synthesized by bacteria are absorbed by passive diffusion in the ileum and colon. Remember last week there was a question whether B12, which is water soluble and synthesized by colonic bacteria, whether it is absorbed. So I did post on Loop that it is not possible, that is used by the bacteria themselves. However, menaquinones, they have got capacity to get absorbed at the brush border of ileum as well as colon. So Mary, definitely go after those fermented foods. Can I request everybody to have themselves on mute, please? Okay, then the same story, they are incorporated into chylomicrons, and vitamin K usually travels with VLDL. That's how it is going to the tissues so that it can be used by the body. Okay. So before we go on break, just spending 2-3 minutes on this case study. Have a read and then reflecting on the absorption pathways that we have just gone through and the cofactors that we have understood and learned today. So try to make a priority list for yourself that if a client is coming to me with deficiency symptoms of fat soluble vitamins, which cofactors do I need to be mindful to incorporate in their diet or as a supplement? So maybe just 1 minute to go through the case study and make a list for yourself. Okay, now I want to hear from you all. What do you think?
I've got potential deficiency in vitamin D because he's got frequent infections, and potential deficiency in vitamin A because of the sudden decline in night vision.
Yes, that's correct, Mary.
That's as far as I really got to.
No, that's fine. Yeah.
But I think I did see that for vitamin D, cholesterol, B2, B3, and magnesium were required as agonists.
Correct.
Is that right? Yeah, as agonists. I always get confused between agonist and antagonist.
Yeah.
And then
So
for vitamin A, zinc, iron, and B3 were also needed as agonists for those coenzymes.
Yes, very good. I was thinking you will forget zinc, but very good. Anybody else would like to add anything? Or...
Being a shift worker, a night shift worker, he, may not get exposure to sunlight, so that would be a factor.
Yes, it would be, definitely. How would we ensure then, like, kind of, what will we tell them? Whenever it's your holiday, go out and sun, or supplements for some time, isn't it?
Yeah.
But it's such a tricky situation. It messes with cortisol, melatonin. And there was a study in CSIRO where they looked at the telomere length of night shift workers. So that was easy. Would anybody like to add or comment anything? Does anybody has a question?
Is it just vitamin D and vitamin A that he is deficient in?
I think the reason I've put it out there is that there is deficiency of vitamin A and E also. Okay. So again, the aim was that we look at all the fat soluble vitamins. Okay. Now Tracy is asking a very good question. Does alcohol interfere with esterification? Would anybody like to comment? Yes, Juliana, that makes perfect sense because alcohol impact absorption of vitamin Bs. It will impact esterification. Number two, all the alcohol affect liver generally, where vitamin A is stored. Vitamin D is activated. So there also it will impact. Plus esterification, it actually degenerates the brush border layer because the toxic metabolites from the liver can travel to the gut. And we'll study about that in session 5. So directly also, yes, and all that esterification is either happening in the intestinal cell or in the liver. So definitely. Okay. Again, requesting everyone to mute yourself. And now let's take a 5 minutes or 10 minutes. Let's take 5 minutes break. And then we come back and talk about macrominerals. Okay, let's restart with macro minerals. So minerals, we divide them into two major classes. Mainly these are inorganic elements and they come from earth, water, soil, plants. When do we classify them as macro? When our body needs it in a bigger amount. So, maybe around 100 milligrams per day. Then micro minerals we can further divide into trace and ultra trace. So trace minerals are required in about 1 to 100 milligrams per day by our body. So that's what its recommended dietary intake is. And then ultra trace are the ones that are required in about less than 1 milligram per day. That's what our human body's requirement is. We all know they are very important, even if they're required in such small amounts. Some of them, they function as iron or in the electrolyte, so they can split into its ionic form that has a plus charge or a negative charge, and then they help us in membrane transport and maintaining osmotic balance. Mainly, some of them have direct interactions, but many a times they can be competitive. Okay. Now, this diagram quite weird, but what does it tell you? What would be your interpretation looking at this one?
They're all like codependent or something.
Yes, that's one aspect. And second would be?
They're all trying to use the same receptors or similar receptors.
Definitely. Thank you. Yes, that's the thing. That they need each other also, but most of them, they share transporters, so they inhibit each other as well. So there can be positive interactions and there can be antagonist interactions. For example, iron and copper. And we'll learn this in detail next week, that we need some copper dependent protein transporters to absorb iron into the blood. Okay. But like zinc, excessive zinc can actually lead to copper deficiency. And interesting fact is that we have a endogenous antioxidant. It is called as metallothionein. And it has both copper and zinc sit together in that enzyme structure. And that protect our body from infections. So it's quite complicated. And we are still trying to understand how body is maintaining homeostasis then, when it is so intricate. Okay. So talking about calcium, most abundant mineral, important for bones and teeth. And it needs acidic pH so that it can be absorbed only as calcium 2+. So that's an important point to take away. Now, these are some of the calcium forms. It is not exhaustive, but this is just some of the forms in which it is available as supplements. So if you find that there is calcium carbonate, then it's possible that it would have 40% of calcium in that entire supplement. But this form is not considered very good because it may cause some issues. If I have a client who is elderly and I suspect that she's a menopausal woman. She may have issue with calcium absorption, and she may not be consuming enough dietary calcium. So my strategy would be to keep her on calcium citrate, because it will take away that dependence on hydrochloric acid in the gastric cells. Then calcium orotate, it is also reasonably well absorbed. And when some people have an issue with some neurotransmitter synthesis, okay, because they are being transferred from one membrane to the other via calcium channels. So at that point, I would like to use calcium orotate. Now coming to calcium absorption. Now there are a lot of words here. I'm again going to go very slow, and you can keep highlighting steps. And you know, I like to go through the diagrams. Now you would notice that how this diagram is different. It is showing actually two intestinal cells, okay? Because it is a whole stack of them lined next to each other in our gut layer. So in the small intestine, if I'm consuming food calcium or I'm containing supplements, low pH is imperative. Why? Because then this calcium 2+ gets separated, and this is now available from absorption. Now there are various ways in which calcium can be absorbed. There are two mechanisms. First one is saturable, carrier-mediated active transport. And this is done by this transporter, TRPV6. It's expanded as something like transient receptor potential vanilloid. I know how tricky it is. I can never remember that one in its full form. Okay. So what do I mean by saturable? That it will take calcium inside if it sends or it is told that blood calcium is low. When there is sufficient calcium in the blood, this one would just sit idle. So that's what when we say it is saturable, saturatable. No, that didn't come out right completely. Saturable, that's the right one. Sorry. Now, can you see there is another mechanism? When we are taking supplement and body needs some more, calcium can simply diffuse in between the two cells. And that is what is called as paracellular diffusion. Okay. So these are the two mechanisms. It might seem confusing because the same process is shown in this diagram, which has two intestinal cells. So I've been asked these questions a couple of times. That's why I'm saying that again. Now, when we say that vitamin D supports calcium absorption, what does that mean? It means is that vitamin D increases gene expression so that more and more TRPV6 is manufactured and it comes on the brush border so that more and more calcium can be absorbed. That's one step. When calcium comes inside, we have a different transporter and it's like a ferry. Okay, this is called as calbindin. This calbindin, it just ferries calcium across the intestinal cell so that it can reach the brush border. I really don't know why it cannot swim on its own, but evolutionary, again, something we have developed over the years. It has a ferry for itself, which is called as calbindin. And this is the second step where vitamin D supports calcium absorption because it increases gene expression or transcription of making calbindin. If I am low on calcium, I am osteoporotic, then vitamin D will ensure that my body is manufacturing more of calbindin. So that even if small amounts are coming in, there are enough transporters to carry it across the blood. Then at the basolateral layer, we have got calcium ATPase that get it across into the blood, and then in the blood it can move around freely, and sometime it may be bound to albumin. Just one more point, that even estrogen is needed. You know, we have sometimes women who are in a postmenopausal stage, we say that they are deficient in calcium, they are prone to osteoporosis. That's one of the reasons, because estrogen, again, there's one more reason, we have estrogen receptors on bone cells. Okay? And the second is that when we are synthesizing this transporter, it is under the command of estrogen also. Questions for calcium absorption? Any confusion? Yeah.
Yeah, I've got one with regards to the two cells that they're showing. The once the calcium's absorbed through the transporter, the receptors internally, the calbindin D, look different. What was the reason for that?
Oh, this one.
So that one's like the shape's different. So we've got the same shape over here on the right, on the top one, as we have on the bottom one, but this shape for this calcium receptor, this transporter internally is different. So unless it changes shape once it absorbs, like grabs hold of the calcium, changing shape as it crosses the cytosol.
Yeah, I see. My understanding is, as it's kind of a shuttle, so there is a place for calcium to sit. Okay, so it carries it, and when it reaches here, it has to release it. So it kind of moves around so that just simply by endocytosis, it can be released in the.
Yeah, I'm not about the release. I'm about the transporter. The transporter has a different shape. Number 2 on both of the enterocytes,
Yeah,
they're different shapes, and I'm just wondering, are they 2 different types of
No, they are not.
transporters? They're
No.
the same?
They are the same.
All right, thank you.
So we can confirm it through the book also. This diagram is taken directly from the book.
Yeah.
It is calbindin, and in my understanding, what they're trying to show is that it has to do a little effort to release calcium. So it releases after facing it towards the basolateral.
Yeah.
But the same thing, yeah.
Okay, thank you.
Why do they confuse us by changing the shapes? Yeah, that's my understanding. It's the same transport.
Yeah. So
Good. Any other confusion, guys? Any points you want to repeat? So now we know why vitamin D is important, why estrogen is important, and at where they are supporting calcium. So Annie is asking that, is it showing that different transporters take it to the blood? No, it is, there are 2 of them. Either it can move around freely as calcium after being transported by ATPase. And this is also showing ATPase. It is the same transporter even at the basolateral layer. But sometime in the blood, it can move around attached to albumin, or it can also move around complexed with citrate, sulfate, or phosphate. So transporter at the basolateral layer is also the same. Calcium ATPase. Yes, Juliana, you are right. TRPV6 are called as calcium transporter 1. So now talking about inhibitors or antagonists. So here we have listed that some factors may help us in increasing calcium absorption. Let's go through them first. So when there is a increased demand, then body recruits more of transporters. Growing children, they need more calcium. Some food components such as protein and lactose, they help to absorb more calcium. And vitamin D, we can add estrogen as well here. We have added estrogen deficiency on the other side, but yeah, it should be here on the right side as well. Caffeine, this one plays, it inhibits calcium. And you know, a lot of fizzy drinks, colas, they also leaches calcium from the bone. Has anybody heard that? Now again, we'll talk about that. Oh, sorry. We will talk about that in last session 13 because, you know, kidneys, they are in a process of maintaining a particular pH in the blood and in the kidney arteries. And when we are consuming a lot of those fizzy drinks that may have some other nutrients or simply sugar, they change the pH. That is not good for the calcium in the bones. Okay, Juliana is saying that this might be incorrect. When I remember reading it last time, the thing is there's not enough randomized control trial in larger populations to look at that acid alkaline feature. But it does play with the pH of the body. And in that sense, it forces body to leach calcium from the bones. That's why it is a risk factor for osteoporosis. But I agree, the research is inconsistent. But again, what I'm saying is when we read about that in session 13, we make our own clinical judgment. Tracy is talking about medications can inhibit absorption, such as tetracycline, often used for acne. Correct. That's also possible. And one of the reason is such as proton pump inhibitors also, because they are changing the pH of the gut. And we have just noticed that we need low pH for calcium to be released from the food and to be absorbed in this area. Okay. And some of the fizzy drink, the reason I was saying is some of the processed food also. Have you noticed how much sodium they have? So in one of the assignments in the human nutrition, when I was in uni essay, we used to ask students to do their own dietary intake and, you know, then put the data in FoodWorks and look at their sodium intake was up to 500 times the recommended dietary intakes, even more. Okay. And you would be doing in your other subjects, you will be looking at dietary softwares for analyzing nutrient intake, and then you would notice all the breads, all the breads, cakes, biscuits, everything has sodium, juices as well. And sodium and calcium have this relation. If there is too much sodium, kidneys have to keep a balance, and then we excrete more calcium. So remember this one, please. Okay. Then if we are, now this is a tricky thing. Magnesium, zinc and calcium, they are all written, sorry, zinc like calcium, they are all written as a competitive inhibitors. How tricky is it? How do we take everything separately? So the thing is, all these divalent ions, they can also compete with each other. Now, just last important thing, how body is trying to maintain calcium homeostasis. There are three main hormones that are involved in calcium homeostasis. One is parathyroid hormone. Then we have the active vitamin D, and then calcitonin, which is released by thyroid gland. So I've added few things here just so that for visual learners, we are able to make connection. So repeating from the absorption slide, that whenever there is low calcium in the blood, body sends message to PTH that directs kidney to start secreting active vitamin D. And what does vitamin D do? It increases carbindin numbers so that more and more calcium comes inside. It also reduces kidney excretion of calcium, and it allows bone resorption. That's why, I have an issue when somebody is on vitamin D3 and we are not ensuring that they are consuming enough calcium, because vitamin D3 can extract calcium from the bones, and it may actually harm if we are not keeping a balance, if there is not enough calcium, because it will get the instruction that there is no calcium. Then calcitonin, it does the opposite. When there is high calcium in the blood, it gives the message to thyroid gland to start secreting calcitonin, and it actually do the reverse of what vitamin D is doing, so that calcium concentration is brought to its normal. Okay, moving on to magnesium. It is the sixth most abundant mineral in the body. It's found in the bones, in the muscles, sometimes it's present in the tissue as well. These are the different forms, and I'm sure most of you would be aware that Epsom salts, which have magnesium sulfate, our body can absorb it via skin as well. And I think it has its origin from Germany, where they used to use it for the first time many years ago. Then magnesium lactate is another important form which is absorbed well. Magnesium citrate, which has about 16% of magnesium in its structure. Coming to absorption, quite similar to calcium. So again, one mechanism of its transport at brush border is by active transport, and it has a different transporter here, TRPM6. So magnesium is also absorbed when it is in this form, magnesium 2+. And these channels can then ensure that magnesium comes inside the intestinal cell. Now you know what does this mean. Okay. Then at the basolateral layer, we have got energy dependent ATPase, which carries magnesium across the blood. And when we do so, one molecule of sodium is coming inside. That's why it is called as sodium dependent ATPase. When in the blood, magnesium moves around bound to albumin or globulins. It can move around freely as well, and sometimes it is bound to citrate, phosphate, or sulfate. So quite similar to calcium. Magnesium factors that may affect its absorption. Protein intake, highly important to consume high biological value proteins that provide enough amino acids so that its transporters are made in the liver and they do their optimal function. Vitamin D is known to support magnesium through active transport. So what does that mean? Vitamin D is supporting this TRPM6 gene transcription. Phytates, non-fermentable fibers, they bound to magnesium. And when this happens, magnesium may be just excreted. Unabsorbed fatty acids. If somebody has malabsorption issues, if somebody has fatty liver, they may actually bind all those magnesium and excrete them in the fecus. So optimal gut health, optimal liver functioning is important. Magnesium is very, very important. More than 300 enzymes, they need magnesium. People who are coming to us with muscle fatigue, muscle pain, think magnesium. People who are coming with depression, think magnesium because it supports those neurotransmitters as well. Okay. Then there is a very intricate relationship between calcium and magnesium. Sometimes they compete and sometimes, in fact, they support each other. Magnesium can mimic or displace calcium from calcium binding sites, thus decreasing its flux across the cell membrane. So tell me, you have a client coming to you, a hypothetical situation, coming to you with, they have been doing a lot of exercise, they are having a lot of muscle cramps. What do? Give calcium or magnesium supplement? Magnesium for cramps. Yes, Annie, Megan, Michelle, you're all right. Remember magnesium. Now tell me, would giving calcium supplement may be contraindicated in any chronic disease condition? Think chronic condition. Can access calcium? We have to be mindful. Very good, Jane. Cardiac diseases, yes. Why? Just again forcing you all to recollect from your biochem. Sorry. Remember when we are making that atherosclerotic plaque? Yes, Juliana, you're right. In that plaque, calcium get deposited. So please ensure that look at person's medical history, heart health, and don't give too much calcium. I would like to again, stay with food sources because body has to do so much to get that little bit of calcium inside. So better to give food sources if they have any such condition. Yes, people on calcium channel broken. Good one. Good, Juliana. There also we have to be really careful. Now there was one question here. We can discuss that one. Where was that? That they compete with each other. Yes, but you have you noticed that some of these supplements, they come together, calcium and magnesium all together. So then they would be in that particular form, which can be easily absorbed, and it would not be in very small dosages, because if it is in small dosage, then body would compete. If it is in high dosage, it will be absorbed by simple paracellular diffusion. It's tricky, isn't it? But again, I don't want you to remember all of this now. I just want that there are some associations made in your understanding. And when you do your clinical subjects, you are able to build on this knowledge. So moving on to phosphorus, second most abundant mineral in the body, and it is present in various forms. When we are talking about our greens and grains, and we are saying that they are really good because they have fiber, at that time we are also saying that their outer cell layer has got phytates and phytic acid. And that is where phosphorus may be present. And these are the same molecules that inhibit calcium and iron, because they form an insoluble complex there. So if I'm consuming legumes that may have phytate, it's better to soak them, okay, and steam it a little so that these cellular matrix, they are broken to release phosphorus and allow for iron and calcium absorption as well. Absorption is influenced by vitamin D, and it increases in sodium phosphate. How does vitamin D support its absorption? By making this enzyme alkaline phosphatase, by increasing the numbers of phosphate transporters at brush border. Okay, and here, this one, this transporter. So organically bound phosphorus, it has to be acted upon by phospholipase. And then we have a carrier mediated active transporter, which needs sodium and is under the influence of vitamin D. That takes it inside the intestinal cell. However, if there is high concentration, then body can consume it by simple diffusion. Sometimes magnesium, aluminium, calcium, they actually bound to phosphorus and they will get excreted because they form a compound. Okay, vitamin D. Is that one now clear? I've repeated that one, how vitamin D is supporting. So vitamin D is supporting because it is overlooking making of phospholipase as well as this transporter. Then in the blood, there are different forms of phosphate moving around. 55% is as phosphate, HPO42 minus. Now we'll talk about this in detail when we do session 13, because these same macro minerals, they act as ions, electrolytes, and they help us in maintaining pH of our blood. And then this form will reveal its relevance. Okay. So right now we remember that it can move around in the blood as HPO4. Sorry, it can also move with calcium, magnesium, or sodium. Now, vitamin D, I've said how vitamin D supports phosphorus of absorption of phosphorus. Can anybody comment by reflecting on session 2? How does zinc support phosphorus absorption? It may be asking too much from you, so apologies, but I just wanted to give somebody a chance if they remember. Remember this alkaline phosphatase? This was used to break away phosphate bond in one of the water-soluble vitamin. This is the one that needs zinc. That's why zinc is a agonist. Okay. Now we discuss in short about potassium digestion and sodium digestion and absorption. As I mentioned again previously in session 13, we'll be talking about them in little bit more details because they have their importance in their ionic form. So potassium is the major intracellular cation. So it is mostly found outside the cell. It decreases urinary excretion of calcium. So if you are consuming lot of potassium, I'm not talking about normal physiological amounts. If you are just consuming high potassium, then it may impact urinary excretion of calcium. Would anybody like to share any functions of potassium and food sources if anybody has heard? Okay, Michelle and Vanessa. Sorry, I'm not happy with that answer. I would like all of you to look at the databases, NRVs, where Australian food sources are given for potassium. Banana is actually considered medium food as far as potassium is concerned. I know everybody says it has too much potassium, but it's only in the moderate amounts. Oranges, dark green leafy vegetables, they may have more potassium. Some of our indigenous foods also has potassium. So please explore that so that we are equipped to make our own clients aware later in future. Okay, Juliana, you're right. It is important for regulation of heart contraction. Now, you know, excess potassium can also lead to heart disease or even heart attack. Hypokalemia, low potassium, can also lead to heart condition. So a couple of years ago, we were talking about this and I had a student in the class who shared with me that one of their family members had a heart condition and they went to a practitioner and that practitioner kept them on high potassium supplements. And when they went back to their surgeon, because that family member had just had a heart surgery. So just trying to understand that a high doses of such simple forms of salts can actually lead to more damage rather than help. So first stay with food sources and then take their medical history and start with a combination supplement or give in low dosage and make client aware that, you know, be mindful if you had any contraindication. Okay. Absorption, again, we are still not sure. We are still discovering what transporters are there or not, whether there are some specific sites from where potassium is absorbed, either in the colon or in the jejunum. But what we know is that we need hydrochloric acid, because then potassium is in this form, ionic form, and then it can go inside. It is suspected that ATPs may be used. It is also suspected that we might be exchanging chloride or hydrogen here, but we are not sure. So one less thing to learn. And that basolateral layer, we have potassium channels. Okay. Now there is something written here. Hypokalemia reduces insulin secretion from pancreas, which in turn influences the carbohydrate metabolism. I don't want you to remember this, but again, just that extra bit, that people who are diabetic, who are insulin resistant, they would also be deficient in potassium, because body is trying to make more and more insulin, and when we do so, we need potassium. Lot of recent evidence coming up that potassium is important for glycemic control in our body.
Can I ask just on the hyperkalemia, are
Yeah.
you saying that it's actually might be a cause of insulin resistance or just in insulin secretion?
Yeah, good point. Actually, it is thought that it is a two-way process. It's both ways. That is, people who are deficient in potassium, they are susceptible to becoming insulin resistant. And when people are diabetic, they are becoming deficient in potassium.
Right. Okay.
Okay. Yeah,
Yeah.
it is a two-way thing.
All right. Thank you.
And Juliana is talking about something. The depolarization of the B cell causes release of insulin. Wonderful, Juliana. That's where potassium may be used. Yes. Anybody else? I hope and nobody is confused. Again, just telling you that this is that extra bit, and save it in your notes about importance of potassium. Last one today, sodium. Please remember it is the major extracellular cation. So, you know, in your multiple choice question in the final exam, you may be asked which one is the major extracellular, which one is the major intracellular. So from that perspective, please highlight this one for your notes. Yes, I've just important thing to remember, which I mentioned earlier as well. Too much of sodium may increase calcium excretion. And again, when I say too much in nutritional biochemistry, I'm talking about supplemental forms or processed foods. Because what I am hoping you all would appreciate is that when body has to take anything out from the food, it does so much work. It goes to extra lengths to do so. So there is very less chance that body have excess from normal food intake. Now, sodium present in every cell, major cation in the extracellular fluid. So no doubt, intestinal cells have actually got more than one transport mechanism in place. So first one is there is something known as sodium glucose co-transport. That means when body is taking glucose in, it can take sodium in as well. Second one is kind of an exchange, a barter system happening here. Okay. So there is sodium hydrogen exchange. So one molecule of sodium goes in and one molecule of hydrogen comes out. So there is some exchange barter system happening. Third mechanism, which has been observed in the colon in the research done so far, is that we have these sodium channels at the brush border. And at the basolateral layer, we have got sodium potassium ATP dependent enzyme, which is facilitating its transport across so that free sodium can move around in the body and cells can use it immediately. Well, that's all for today, but let's clarify any doubts if we have any questions, if we want to discuss anything else. We have some time now.
Can I just ask, when you mentioned about the bananas and potassium,
Yeah.
You said to look up the NRVs.
Yes. Okay.
Give me a little bit more information where I can find them, please.
Yeah. So you have to type Food Standards Australia, New Zealand, and look at NRV. Okay. Oh, I think I've typed it only to one person. Just a sec. Just typing it for everybody to see. So see, again, when we are talking about local produce, we are trying to think about indigenous foods as well. This has exhaustive data. You simply have to go in, type potassium, and all the foods that are the richest source of potassium to the lowest source would come up. And you may notice that banana, they are good source, but they come under moderate source. So there are some other food sources that are rich in potassium.
Okay, great. I'll check it out. Thank you.
Good. And again, it's a good strategy. If you're making that table, making that food sources in that list, have it there so that when you are in the clinic, it's already there. You don't have to go and look around, spend time on Google search. Your table is ready to be copy and pasted for your client.
Can I just ask about your comment about Indigenous foods and these particular nutrients? I'm thinking those guidelines, the NRV guidelines, are actually, like, they generally mention supermarket foods, but when you are talking about Indigenous foods, specifically, because I'm interested in that, where would you look for that information?
It's very hard, but when I was doing medicinal food science, and I noticed that in NRVs only, the data is added now. I keep forgetting about the name of that food, but there is one which is rich in potassium as well as vitamin C. And there's a lot of research done that it has. Thanks, Vanessa, for posting that link. So that food has 100 times more vitamin C than any other fruit. So again, they are updating it. They're doing it very slowly, but unfortunately, we don't have a separate database for those foods. It's a work in progress, and this is my small way of motivating you all to maybe do a little bit more research and contribute in some way so that those foods are, given their proper place in the food tables. But sorry, I don't have any link which I can recollect yet to.
All right, thank you.
Any other transport mechanism, any confusion about the transport you want to ask? Because you know that we have discussed some very important cofactors today. And it will stay with you if you again do that exercise of doing your own revisions. Okay. Do the post-lecture quiz. Let me know if you find any issues there. If there is a mistake, let me know. And post any question on Loop. So far, I've got a couple of them. I like to find some of these indigenous food sources as well. I'll find the names and put some of them. It is somewhere in one of the folders. I'll try to find out about how to keep a balance of not getting cancer and still getting enough sunlight exposure. And I'll also confirm regarding fermented foods, whether they are a good source in enhancing our vitamin K status. So these are the 3 questions in my list that I have to do research on. Any other comment, any feedback for me? Okay, one more query. Have you started looking at the assessment 1? Question 2?
No.
Okay, if you haven't, do it somehow this week, because next week we'll be talking about iron. So that's the rest of the 2 questions for your next assessment. So then I would like you to focus on that. So it's a good idea to get over with question 2 this week. Okay. Well, thank you, everyone. That's all for today. See you next week. Bye.